Hi guys, so today we want to continue with the sound, traveling waves and sound. So basically today we are going to look at the sound part. In the last lecture we talk about the traveling waves, right? So we develop a general description of the wave that is applicable to a variety of situations. We also derived an equation for determining the speed of the traveling wave on a string, and then we found that the speed of the wave on a string is b equal to the square root of Ts divided by m/L, or I wrote mu, right? So mu equal to m over L. That's what I had. That's the linear mass density. Okay. We also looked at a few examples of two-dimensional and also three-dimensional wave. And then we came up with the mathematical description, right? We actually even did the equation here, so I'm going to just put it over here. Right, so you also determine the so we also wrote the mathematical function that it fit to this curve, and we found that this is a function of both the position and time, yxt equal to a sine 2 pi by lambda times x minus 2 by ft. Okay, and then you guys also remember you found a, lambda, f, and t. So that's what we did. So we also looked at the summarize. We also looked at the electromagnetic spectrum. We say the speed of the speed of the light is 3 into 10 to the power 8 meter per second. And we said the light is a form of electromagnetic wave, and then we look at the electromagnetic wave, different types of electromagnetic wave, right? Like, so we have radio wave, microwave, infrared, visible, ultraviolet, X-ray, and gamma ray, and we looked at that. They range from 10 to the power 4 hertz to 10 to the power 20 hertz, right, in terms of frequency, and then in terms of wavelength they start somewhere around 10 to the power 3. I mean they start at 10 to the power minus 12 meter all the way to 10 to the power 3, so 3 meter. Okay, and then we looked at whenever there is a higher wavelength, lower frequency. Okay, so those are the things that we looked at. So today we look at this sound wave. So right now I'm speaking here, right? So here is an example. We have a speaker. The sound is projected. Whether a speaker projects the sound, produces the sound, or my mouth produces I'm producing the sound, then it's this same phenomena is happening, right? So here, as we speak, what happens is there is a disturbance in the medium, right? That's what the wave means. But then what happens is the air molecules, they vibrate. Basically they collide each other, and then some of the air molecules, they get together, right? And then that's called what? They get compressed together, right? And then they also, some of the air molecules are kind of far away. So there is different region here. So, and then these are these regions can be represented as a trough here, which is the peak, right over here, amplitude, and then this point where the molecules are farther away, that can be called as a crest. Okay, So those are the two things here to remember, to note down. So where, so trough and crest here, right? So we can essentially, how can we hear the sound is basically, at least from the physics perspective, is because when the sound is produced, there is some disturbance in the medium happens, and then air molecules, they collide, and then they reach to the eardrum, and then after that we will hear the sound. Do you think we can hear all the sound? All the sound. I mean, small, really quieter sound to loud sound. What do you think? At home, have you noticed like how many sound like are there, like like refrigerator is making a sound like a like that. Something else is making other sound, right? So a lot of sound, and maybe there are really sound we don't hear it, right? So it turns out that the sound waves that human ear, or the range of audibility of a human ear, lies between frequency 20 hertz to 20. Oops, sorry about that, guys. 20 kilohertz, okay? So 20 hertz to 20 kilohertz. So the frequency that is smaller than 20 hertz are called infrasonic sound. A frequency greater than 20 kilohertz, so greater than this value, are called ultrasonic sound, okay? So this is infrasonic, this is ultra, okay? And then the human ear is, possible, individual ear is possible, it can hear, detect sound, any sound between 20 hertz and 20 kilohertz. But then there are other, like animals, and then, other animals, they can hear the sound that we cannot hear, or that's not audible to our ear, basically. Okay, so this is something I'm going to write this down here on the board for you guys. So how do you think what property determines, what quantity do you think is responsible for a speed of a sound? What do you think? Do you think the density of we talk a little bit, we touch about it, right? We said there is, vibration, a collision of molecules. Do you think the density of the air matters? What do you think? What do you think would happen? Maybe the temperature would matter anyway? What do you think? So speed of sound, okay? So speed of sound relates it is related to the speed of the molecules of gases, basically, okay? Because why? Why do you think that's the case? Think about it. Wave or sound wave, it's also a form of energy, okay? It's a disturbance, but it needs, the energy is needed to transport this wave, right? Okay? So molecule needs to collide each other to transport energy. That's the idea here. So if you guys remember from chemistry, you guys remember this root mean square speed? BRMS equal to square root of 3 kb T by m, where m is the mass of the atom. Kb is the Boltzmann constant, T is the absolute temperature. okay, in Kelvin scale, right, in Kelvin. So this is something from chemistry. It turns out that actually speed of sound is also given by very similar equation here. So speed of sound V, let us just be, let us call B sound or BRMS, I guess you could say this. BRMS is given as this BRMS equal to square root. Similar to that, not exactly the same, but something like this. Gamma KBT over M. Okay? So, I'm going to erase this part, okay guys? This looks similar to you guys now. Other than except this 3, right? In place of 3 we have gamma there. So this gamma is equal to 1.67 for monoatomic gases. Example is like, you know, like, do you guys remember helium? I'm just writing He, okay? That's just the example. Let me write easy means example. And then gamma equal to 1.4 for diatomic gases. Diatomic gases are like what? Oxygen, nitrogen, etc., right? And then gamma equal to 3 that you saw earlier for triatomic gases, example like carbon dioxide. Okay? So I'm not going to write that one, but this should be sufficient. So the speed of sound is equal to square root of gamma kb times t divided by m, where my m is the mass of the molecules. Gamma is, you know, a constant, and then its constant value is 1.67 for monoatomic gases, 1.4 for diatomic gases. Kb is Boltzmann's constant. T is the temperature in Kelvin scale, absolute temperature. Okay? So now there is really it has nothing to do with the density of the gas. So the speed of the sound does not depend on density. Okay, it does depend on the temperature. This is the important thing to note there, and it depends upon the mass also, mass of the gaseous molecule. Okay. Excuse me. So you guys may be wondering, you know, like, well, then what do you think is the speed of sound in air? Okay. So speed of sound in air is 343 meter per second. So V RMS, or let's write sound. It's a sound here. You could also just write RMS here, since we just said RMS. Or you could just say V. So always look at in that context, okay? V sound is 343 meter per second. See, here is an example of like thunderstorm, right? So lightning happening. So when the lightning happens, we see some light, the speed of the light is different. We already looked at that in the electromagnetic spectrum, you know. But then the speed of the sound we hear is actually 343 meter per second, a lot lower, right? The sound we hear is a lot lower than that light, speed of the light, okay? So 343 meter per second, this value is an accepted value. This is considered to be the speed at temperature 20 degrees Celsius, okay? So like in 20 degrees Celsius, this is what we consider as the speed of sound in air. Okay, so next topic is sound intensity. intensity represented by capital I. So for example, let's say we have some, speaker, right? Like let me, so I don't know what to play here. I don't have, maybe I can find something here to produce sound. Just give me a moment. Let me see if I can play something. Oops. Physics. Okay, that's the ad game. So let me see if I can get that. I just wanted to explain this. Okay, sorry guys, I didn't want this ad to show up here. Okay. So some sound, okay? So you can hear my speaker is somewhere around here. So if you have your speaker, we have a speaker and we are playing the sound. Usually sound kind of, the sound is traveling in all directions. So imagine, let's say we have a source here. Source of the sound is this dot, okay? So this is the source. And then let's say the sound wave is, it's going in all directions, all three-dimensional direction, okay? So that's called spherical wave, okay? So spherical wave. And then if we want to make that sound, right, like, so maybe easier way for you to visualize is like, speaker here, and then it's producing sound. The sound is going everywhere, as in like that, okay? Or maybe it is easier if you have a light bulb, how the lights are going in all direction, right? But then how do we know where the intensity is stronger, okay? So what do I mean by that intensity? So let's look at that, okay? So the sound intensity, so if we have a source here, and then I'm going to draw some distance, maybe I'll draw over here so we have a little bit bigger. Here is a source, I have some, so let's say this source is producing some sound, and it is, it is propagating in all direction. And then let's say we want to look at some distance here, R1. What is the sound over there? What's the intensity of the sound? Because if you sit here, the sound, you're like, the intensity of sound here, and then if we look at somewhere at this point, let's call that as R2 distance, the intensity will not be the same. What do I mean by that intensity anyway, right? So okay, so to talk about the intensity, what we could do is we could, just make another circle here. This looks circle here because it's a two-dimensional surface. It's actually sphere, okay? So it's like this is sphere, okay? Imagine sphere, imaginary sphere of radius R1, okay? So we can define the intensity I as power per unit area. Power, what is the power? Amount of energy spent in transporting the wave in a unit time, right? That's the power. And then this intensity is a ratio of the power per unit area, okay? So in this case, so at this point, I1, let us say intensity 1, and at this point we can hear two different intensities. We have an intensity I2. Obviously, just even looking at this, it's obvious that intensity at I1 would be different than intensity at I2. What does it mean? I am making this, imagine this is sphere here. In this sphere, let's call that's it's at the radius R1, okay? So at that boundary outside, the intensity is smaller. Intensity is I1. But if I make a bigger sphere, intensity is I2, which means intensity in the outside should be, the bigger, sphere should be, on the surface of bigger sphere should be smaller, right? So let me check my video. Okay, it is still there. Okay, so I is the intensity, right? So the unit is then what? Power is measuring watt, area is measuring meter square. So watt per meter square is the unit. Okay, I'm gonna do. I'll use this figure again for in the second video. Okay, so for now just look at this. So sound intensity, it's the ratio of the power per unit area. Unit is watt per meter square. Okay,